And here we go, guys. Question 8. So this is the final problem of the paper. And this looks like a two-particle pulley problem. So let's check it out. Now, according to the information below, we have two particles A and B that have masses 2m and m respectively. So this means that A, we have a weight of 2m times g, so 2mg, and here mg. Okay. Now the particles are attached to the ends of a light inextensible string. Now, since this is a string, we can assume that there's tension coming off it. So let's put T there and T there, and it's the same string, so tension should be the same for both, really. Now, what else we know? Particle A is held at rest on a fixed rough horizontal table at a distance d from a smooth light pulley. So first things first, this is a rough table, so we have to assume that there's some frictional force coming off it. So we can call the force coming off at F, but let's see which way it's going. Just by the shape of this, I'm just going to assume that the particle B will drop, but let's keep reading first. Okay, so on. So the coefficient of friction between A and the table is mu, okay, as usual, where mu is less than half. The string is parallel to the table from A to P, so that looks quite clear as well. And pass over the pulley. Okay, so carrying on where we left off. So just to make it quick, particle B hangs freely at rest vertically below P with the string taut and at a height h. So taut just means that the string is completely straight, it's tight more or less. So as B moves, A will move freely. If the string was slack, meaning it's loose, then there's no tension in the string. So think of taut as there being some effect to the string and a particle, so it has a tension. And yeah, the rest of it seems quite obvious. Okay, now here we go. So particle A is released from rest with the string taut and slides along the table. So this means that the direction of motion, let's call it A, and I'm going to change the color, is going this way. So here's A, meaning B is going to fall down towards the bottom. So, alright, not bad. So this seems okay so far. So this is the pressure. Since the weight is heavier here than here, if we let go of A, then B will just drop, and meaning A will drag along as B goes. So they're moving at the same constant acceleration, and technically the same speed until B hits the table, until it hits the floor, I mean. So, alright, so we're good now. Oh yeah, also the frictional force is backwards because, well, it's dragging along, and the frictional force is always, the direction of motion is always away from the acceleration, so it's always pulling back as you're dragging. And yeah, I think we're good now. So how about we go ahead and resolve this, yeah? Oh yeah, and let's add a reaction force, why not? So A and B, so write down equations of motions for A and B, and then show that until B hits the floor, the acceleration A is g/3, 1 minus 2 mu. Let's go ahead and do all of this, yeah? I think we have enough space to do it here, actually. So let's write equation of motion. So at A, we can do it here. So at A, what do we have? Let's have a think. So if we're going to resolve, let's resolve vertically, yeah? And because it's vertical, the acceleration is moving horizontal, so it's perpendicular to acceleration, so there's no acceleration. So B R must equal 2mg. Now if we resolve across towards direction of acceleration, so towards this way, we should have T minus F, and this must equal mass times acceleration, so 2m times A. Alright, I think that's all we can do from here then, and we already know what F is. F is also equivalent to mu R, and mu seems to be fixed, by the way, according to the text. So it looks like we're going to have a solution in terms of mu as given by here. Now let's look at the second equation for B, yeah? So at B, what do we have? If we follow the direction of motion of A, so that is going downwards, we can say that we have mg minus the tension, and this should equal mass times acceleration. Perfect. Now that's done. That's the easy 4 marks. The main bulk comes from finding an expression for B, which is that. So let's do that, yeah? So straight away, what we could do is, firstly, my personal advice is to eliminate tension and make acceleration subject over here. So for the second equation, if I make T the subject, by plussing T and minusing ma, we should have T equals mg minus ma, okay? And now we can substitute this back into this equation. So now what we're going to have? We're going to have T replaces to be mg minus ma, F replaces to be mu r, so it'll be mu times 2mg, and this must all equal 2ma. So the dot here means just multiplying, yeah? And what can we do from here? Well, I would personally collect like terms, and actually first I'll cancel the m's because every single term has an m, so this goes, this, and this. And now plussing a across and simplifying the rest, we should have g minus, what do we have? 2 mu g should equal 3a. Okay, so that's just some quick algebra. So plus a across, that becomes 3a, and collect terms. And now to make a the subject, well, just divide it by 3 and then factorize g out. So we should clearly have this solution. So we're going to have now a equals, firstly, factorizing g, so we're going to have 1 minus 2 mu. So it'll be g over 3, 1 minus 2 mu, just like they wanted. Okay, let's look at part C now, yeah? So find in terms of g, h, and mu, the speed of A at the instant when B hits the floor. So all this is effectively saying is find the speed, because we know the string is tall, A and B is moving at the same time. So this means effectively as B hits the ground, the speed of B as it hits the ground will be the exact same as the speed of A as it moves. So A would probably be somewhere here, traveling at a distance of h, and this will be its final speed. Remember, the particle is released from rest, so the initial speed was 0. So technically the initial speed of V was also 0. So it's actually identical. As soon as B moves, A moves. When it hits the ground, well, I'm guessing the string might become slack, possibly. Now what do we know? So we know that the initial speed is 0, the final speed is V, and the distance traveled is h. And we also have a constant acceleration, thanks to part B. So let's write all of this down below here, yeah? So we have acceleration given to be this. We also know that the distance is h. The initial speed u I mean, is 0, and the final speed is something we're trying to obtain. Now, what Suva equation can we use with S, A, U, and V? Okay, so just having a careful think about this, the most relatable equation I can think of would be the V squared minus U squared equals 2AS. And I believe this is the perfect one. So let's go ahead and use that, yeah? Okay, so what do we have? So we can say straight away that plugging everything in, we can have V squared equals, and then plus U squared across. We're going to have 0 squared, that cancels out. So 2AS will just be 2 times G over 3 times S. So it'll be, so 2 times H, so it'll be 2 times S, so 2 times H, so it'll be 2H, and then we have 2HG over 3, 1 minus 2 mu. I think that's it. Oh yeah, and then to find V, just square root that. So V equals the square root of, well, all of this. Yep, looks good to me. Okay, let's finish this off now. So the final two parts. So after particle B hits the floor, particle A continues to slide along the table. Now given that mu equals a third and that A eventually comes to rest at the pulley, find D in terms of H. So they actually give us a lot of information here. So at this point, what we're trying to effectively say is that A comes to rest at this pulley here. So this would be the final resting point. So let me change the color so it doesn't mix up the rest of the diagram. So here's the final resting point. And now notice how when B hits the ground, well, we don't know if it's still bouncing or not, but I don't think it really matters. The whole point is that the string is now slack. So when something is slack, it means the tension in this case is useless. There's no more effect, so it's technically 0. So what we could do is firstly rework out the acceleration, because now we know that the particle is slowing down. It means there's a deceleration, so we need to find a negative acceleration. So let's resolve again with this new diagram. So I'm going to redraw it underneath here. So this would be in the original particle. We had a mass of 2mg here. We initially had a tension T, but now it's 0, so it's gone. So we can even rub this out completely. We still got the frictional force behind it because, well, you're on a rough ground. Okay, so that's a frictional force. Just make it look neat. And we still got the reaction, which is R. So everything is the same. R is still equivalent to 2mg. F is still mu R, which is technically 2mg mu. Okay. The only difference is, so now it's traveled along some distance. The distance is actually traveled here is from here to here. And the question wants us specifically to find D in terms of H. is the difference here. So what is the remaining the distance here? Well, he's already traveled h across, and he's still got d minus h left. So just because if you think about it, h plus d minus h gives us the total d. Yeah, so that's what it is. So that's our new distance. So let's put that there. So it's going to travel distance of d minus h across, and it's eventually going to reach over here, and that's when the speed will be 0. And this is some point. So let's call this point here firstly c. Yeah? So it's currently at c thanks to the instant when it hits the ground, and the speed of here is the same speed it was at b. So speed of a, what did we say it was? We said this was the speed, yeah. So let's call this the speed at c now. So this is the speed here, vc. Alright, so it looks like we have pretty much everything. And just to recap what we're trying to find again, we're just trying to find the distance. And we need a new acceleration. Okay, so on recalculating the acceleration now, let's do it, yeah? So acceleration now, new acceleration. So we can say, firstly, resolving this one, we had this. Now resolving towards the direction of motion this way, we should have firstly only minus f, and this should equal 2ma. And yeah, is that what they want in terms of m as well? So f we said was a 2mg mu, so it would be minus 2mg mu equals 2ma. The 2m both cancel out, so you're left with minus g mu equals a. So the acceleration is simply the gravitational potential times mu. Gravitational potential. It's just minus g times mu. Sorry guys, just feeling a bit tired. I've just been recording all day. So let's label everything. So that is the new acceleration. So now we have acceleration check, the distance s check, the initial speed vc check, and the final speed 0. Perfect. Let's do this. So I'll write it again here. So this was d minus h. Initial speed was vc, which is all of that. 2hg over 3. 2hg over 3. God, how can I forget? 1 minus 2 mu. Square rooted. And we also have the final speed, which is 0. So now at this stage, we can just repeat the same formula as we did previously using the v squared minus u squared equals 2as. Why? Because we have all the necessary variables. So let's do that. So using this and plugging everything back in, so v is 0. So v 0 minus u squared will just be the square of all of this, which is just simply 2hg over 3 times 1 minus 2 mu. And now we've got 2as. So let's have a look. So 2 times a is minus 2g mu and s. So it'll just be minus 2g mu times d minus h, which is s. Right. Okay, so it looks like we've got to do a bit of manipulation, because the objective of this is to firstly make d the subject. It looks like we're going to have to eliminate, everything will be eliminated. So let's have a look. First things first, looking at both equations, g will be eliminated. We can just cross it out, because they both multiply to itself. The negative signs can cancel out. 2 can cancel out. Yeah, I think that's it for now. So let's expand. So we're going to have, on the left side, expand the bracket, h over 3 minus 2 mu over 3 h, I can't forget that, equals, and then here we're going to have just mu, so it'll be mu d minus mu h. Okay. Oh yeah, we also know, I forgot, mu is also 1 over 3, yeah? That actually helps a lot. So given that mu is 1 over 3, let me just help you. Let me just expand this right now. So if mu is 1 over 3, we're going to have h over 3 minus, let's see, 2 times 1 over 3 over 3. So all that becomes 2h over 9 equals, this becomes 1/3 of d minus 1/3 of h. Alright, now collecting like terms for h, so we're going to have h over 3 minus, so 1/3 minus 2/9 plus 1/3. So 1 over 3. Bear me a second, I'm actually writing all this down. That's 1 over 3. You should get Double checking. Let me just see that again. You should get 4/9, so 4/9 of h, and this should equal 1/3 of d. Now we have to make, just recall, make d the subject, so simply just divide 1/3 across. So be answer divided by 1/3, 4/3, and that's it. D equals 4/3 of h. And yeah, makes sense. D has to be a bigger value because h is just a small quantity. And I believe that's it. And now for the final statement, describe what would happen if mu is half. Well, if mu is half, let's just see what happens. Just look at this VC for a second. If you substitute mu is half here, you'll get 1 minus 2 times a half. That will equate to 0. So you're going to effectively have 0 times this quantity, which will be 0, meaning the speed at this point was 0, meaning it's never reached this point. If you put 0 for the very beginning, you're going to get again 0. So what would really happen, you're going to have an equation with zeros. And you're going to have no acceleration and effectively no speed. So technically the particle of A will not move. Therefore B will also not move. So nothing moves. It's in something known as limiting equilibrium. And that's it, guys. I hope this all helps.